Corning Incorporated, just down the road. So Corning make and design specialty glass and ceramics. So for example, I just looked up, my actual iPhone has this thing called Grenier glass on both the front and back, and that's made and designed at Corning. Jason did his undergrad at the University of Waterloo, and then his PhD at the University of Toronto, and a postdoc at UC Davis, and then in what's called ultrafast lasers, which is hopefully a technology that could be used to cut Gorilla Glass finely. And he's become a world leader in this technology, so he's at Corning developing it further. His trip here has been funded by Engage Cornell, which is an initiative that's been run from the math department and operation research here to help engage applied math undergrads and graduate students with the local community and industry. So this will be continuing next year. And if you have any ideas about how you would like to increase engagement in applied math, I would love to hear your thoughts. So without further ado, please take this away.
Thank you, Alex, for the kind introduction, and good afternoon, everybody. It is really my sincere pleasure to be here in front of you and share something that I'm very passionate about, which is laser material processing, specifically ultrafast laser material processing. And I hope today to share with you some of what the state of the art is or what's being done right now, and to kind of motivate that there's really a lot of underlying mathematics and a lot that mathematicians have to contribute to these areas in a collaborative manner with engineers and physicists. And maybe you'll be happy about this or disappointed, let me know, but there are no mathematical proofs today. I do not endeavor to teach anyone in this room anything about mathematics. That's not my subject matter expertise. I do try and bring to the surface some of the mathematics that are used that may be relevant to some of your areas, maybe something you've touched on tangentially or studied in the course, and that's great. Yeah, so without further ado, the last thing I'll mention is I do work at Corning Incorporated right now. Today, not here giving a presentation about work that I'm currently doing at Corning. There's a process that one has to go through to do that, and the slides get locked a month out and probably redacted beyond the point that I would be able to give a meaningful talk today. So I chose to talk more generally about industry things and some things from my academic experiences in the past and my assessment about some of the things in industry. So my introduction was briefly touched upon. I'll just add very briefly a few things. All three of my degrees are in electrical engineering. The first two were at the University of Waterloo, not so far from here. And I also did a certificate in university teaching during my master's there, and I'm really passionate about teaching and education. And so I really enjoyed these opportunities as well because of that. My master's was on applications of pulsed electric fields, so still kind of in electromagnetics, somewhat related to power electronics. I was applying high voltage electric fields to cells to open up their pores and then do things like gene delivery or drug delivery, just generally speaking. And then in my PhD, I focused on femtosecond laser writing of optical circuits inside of optical fibers, and I'll touch upon that in some of my work today. And then my postdoc was still in femtosecond laser writing, but rather than making circuits on a very small scale of 5 or 6 maybe waveguides or optical components, we were trying to scale that up to thousands or 10,000 waveguides or optical devices all on a small chip, so much larger scale. And that was fairly exciting. And then after that was completed, I did join Corning in the laser processing and engineering team. And basically our mandate, our R&D towards novel laser processing capabilities that are aimed towards creating new products and new manufacturing processes. So the objectives for my presentation today will be to overview several research and industrial applications of ultra-short laser material processing. And I want to motivate the need to build fundamental understanding of the laser material interactions and processes involved in this. And that involves introducing some of the mathematics that lay behind here. And basically, I want to convey some of the needs and the opportunities that you guys potentially as applied mathematicians would be able to explore in this area. if that was your interest, for example, or to try and identify some of the current issues that we're having, and maybe you guys can think of, oh, well, we know how to model that, or we know the mathematics that could be employed here favorably. So to achieve these objectives, the outline for the talk will be as follows. I'm going to provide a little bit on the motivation and the importance of laser material processing. I'm going to talk a little bit about what a laser is and how it works at a very high level, something that you'll probably be able to tell your friends or colleagues that are in non-science backgrounds. So I hope to give a little bit of knowledge in that manner today. We do get into a little bit of math, which is some partial differential equations for Maxwell's equations. And specifically, I'm going to talk a little bit about some of the terms that we need to invoke to explain nonlinear optical phenomena that these ultrafast lasers do. We do not take a deep dive into this, nor is my background really poised to do a deep dive into this, but some introductory level that we perhaps together could walk through. I'll talk about how ultrafast lasers generates these nonlinear actions. You really need these high intensities that one achieves with ultrafast lasers. And I'll overview several what I think are really interesting and relevant applications both in industry and in research of this ultrafast laser material processing. So while you're in this talk, I have a challenge for you guys or something for you to reflect upon and perhaps even comment or ask questions about, and that is try and ask yourself what type of mathematical concepts or models you could employ to explain what's going on or to contribute in some way. Or if I mention here's some of the challenges we face, or as I present some of the equations, what are some of the math that you can help employ? Because I present some of the base cases, but the real world has all of these extra terms and complexities that I think really require someone with strong expertise in math that I would expect you guys can bring. So that's where I hope that this talk can go today. So we're going to start with a little bit of math, perhaps math that people enjoy, money, talking about money. And I don't mean to motivate this field or anything by money. I simply want to convey a point that this is really becoming a relevant field. And so what I'm showing here are the worldwide commercial laser revenues for some 20 years or so here plotted. And around 1960, Theodore Maiman, we'll encounter him later in the talk, was the first to build a laser, a real working laser. And right around that time, he said, I think we have a solution that's seeking a problem. And today I reflect on this chart and say, I think we definitely found some problems to solve based on the number of sales in laser revenues. This is just the revenues for the laser itself. This is not the laser system, the motion control stages, the optics, the endpoint applications or products that they're encapsulated in. Very interesting, there's a spike around 2000. That was the famous dot-com bubble. We thought the internet was going to go much crazier than it did. It got there eventually, but not right at that time. And the blue part is showing diode lasers, which are a subset of lasers that are very relevant in the telecom. They generate the encoded light signals that we read down optical fibers. And so there was a miscalculation there in how many they would actually need. That tailed off and corrected itself. The photonics industry as a whole has over $1 trillion revenue. It reached that point in 2017. So lasers have found many problems. There's a Nobel Prize awarded for the laser itself, and many Nobel Prizes coming afterwards that were enabled by laser and laser technology, including this year's Nobel Prize in Physics, which was for chirp pulse amplification, which is relevant for high intensity or ultra short pulses. So lasers have found wide applications in material processing. So out of that, in 2017, that revenue, you can look at the piece of the pie that is material processing. The next largest sector is communications. And so this is our internet and the way we communicate through optical signals. But laser material processing is very relevant, and there's a lot of applications. And perhaps you'd even be surprised the number of things that are in this room or that you own in your homes that have had laser processing with them. So just very briefly, it'd be nice if you don't know already what a laser is and how it works at a very high level. So laser is an acronym that stands for light amplification, by stimulated emission of radiation. And what's different about laser light than lights from this room, for example, is these four main properties. It's monochromatic, it means it has one wavelength, one color. It is directional, and it is in that it travels in one direction. All the photons travel together. And it's coherent, which means that they are in phase, you can say. The waves start, all the different photons are in phase. They all oscillate at the same start and stop point as each other. And because some of these, you have a lot of power or intensity in a very directed focus. These are very bright sources. So a 100-watt light bulb you would find in your house, a 100-watt laser beam is really something that's a lot of power because it's all focused and concentrated in a small area. So it's often fun when you can go all the way back to Einstein in a talk to explain something. And so in this case, we go back to 1917, where Einstein lays the foundation for the laser. He didn't know it at the time, but for the concept of stimulated emission, and that's actually part of the acronym in laser. So what is stimulated emission? So just some very basic level physics here. If you shine light on a material, you can convince some of the electrons to go from their valence band, where they're static, to a conduction band where they have the opportunity to move. And over time, energy likes to return back to its normal state, the natural ground state. And in that process, the electron will emit a photon in that, returning the energy back and conserving everything. And that's called spontaneous emission. Well, it turns out if you have a photon that's already in the excited state and another photon comes by, through some physics that I won't get into, there's an interaction that takes place, and that one incoming photon will kind of, let's say, convince the other photon that it should start to propagate back, convince that electron to give off its energy in the form of another photon that has the same wavelength, the same coherence, and the same direction as the incoming one. And so this is the concept of stimulated emission. So it's an emission of a photon that's been in a stimulated way. And so that's necessary for making the laser. Now, it was some 40 years later, where at Columbia University, two fellows here, Arthur Charlow and Charles Towns, published a key paper that led to the development of the laser, and it was called infrared optical lasers. So they had the idea, the concept of how to make a laser. They were just working at microwaves frequencies so that they could do this with the technology that they had. So 40 years later, it was like, oh, we can actually use this to do something. And then it still took another 2 or 3 years before Theodore Maiman, working at Hughes Laboratory in California, was able to build the first visible laser, and it was a ruby laser. So that's, in short, the brief history there of the laser. So here are the basic components of a laser. You have 3 main components to build a laser. One is the gain medium, which is some material that you will put energy into, and in the hopes of giving off light. I guess in theory, any material would work. If you give it enough energy, it'll shine. But we tend to choose materials that are preferential, that have a high efficiency in doing this, or have wavelengths of interest, and that are suitable for this. So that's known as the gain medium. And as I inferred, that you need to give energy to this medium, and we call that a pump source. And so that pump source can be a flash lamp, it can be another laser. I guess heat's not so efficient, but electricity works as well. And so this pump source then starts the process of the absorption of electrons to the higher band, stimulated spontaneous emission, and then stimulated emission. And then in order to get the gain to build up sufficiently, they put what's called an optical cavity or a resonator, which is basically 2 mirrors around that you can see here. And what will happen is the photons will bounce back and forth between these mirrors. What the mirror on the output here is not 100% reflecting. It's a high number. I don't know exactly what it would be, but let's say in the mid to high 90s%. A small portion of that light goes through, but the rest of it resonates back and forth and gives your gain. So this is the very simple explanation of how to build a laser. Perhaps if there's some interest, we can talk just some of the modifications that you need to make pulse lasers and specifically ultra-fast lasers. The one hint that I'll give there is the selection of the material needs to have a high gain bandwidth. So it needs to have a lot of frequencies in order to be able to compress that pulse. And so that would invoke a mathematical concept of Fourier transforms. So the relationship between time and bandwidth. If you understand that, you'll understand why we need to have a very large spectrum to compress very short pulses in time. So why use lasers for material processing? It's non-contact, it's clean, it's fast, you can get small feature size on the order of the wavelength of light, you can do rapid prototyping, and you can have strong material interactions, and you can start to process very difficult materials. And so more specifically today, I want to motivate, well, why are we using ultrafast lasers? And so I don't know the technical definition, but typically when one says ultrafast lasers, typically in the literature we see less than 100 picoseconds, more commonly 10 picoseconds and under, but there's some threshold, it's not so important where, but on this scale, let's say. So what's interesting here with ultrafast lasers, we'll talk through this in the next few slides as well, is that you can have a nonlinear absorption. So you can make a wavelength that would not be absorbed in light become absorbing through some nonlinear mechanisms that we'll touch upon. And that allows you to do three-dimensional processing. And these short pulses, basically you're hitting your target for such a short amount of time. There's a very small heat affected zone, and so there's this concept of cold ablation. It's not truly cold, but it's cold in the fact that there's not a large heat affected zone that you get at longer pulse wavelengths, longer pulse durations. And that also allows us to do cleaner ablation as well. And here, you can actually beat the diffraction limit, so you can actually get feature sizes that are smaller than the wavelength because of these nonlinear interactions. And you can also, and I'll show some examples of this, permanently change the refractive index of the material in this manner with ultrafast lasers. So here's a little bit of math just to kind of show some of the governing equations for waves and wave propagation inside of media, which is very important to understand and even model as we go towards real modeling and understanding real laser material interactions. In the box here I have Maxwell's equations. I'm not going to go into the depth of this. There's a bit of physics in interpreting these, but you'll probably at least understand what's meant by the curl or the divergence of a field. And so we apply these to electrical and magnetic fields. Here's, if you take the curl of this equation here, you can walk yourself and derive the wave equation. And so this wave equation governs how electromagnetic radiation propagates in a media. And on the right-hand side, you have this term, P, which is the polarization density in the equation. And normally, in a lot of classical introductory physics or electromagnetics, you'll stop with just this linear term. But in fact, materials have these nonlinear coefficients or terms. The materials inherently are nonlinear, but these coefficients are so small that, and they're proportional to the electric fields, that unless you really have a high electric field, to turn on these small coefficients, we typically don't see them. And so it really took short pulse lasers to get us to a point where we will have the intensities to be able to turn on these nonlinear effects. And so this is an example here of a power series or a Taylor series expansion around this, where you would go and be able to kind of create this equation. So we have a question, please.
Yeah, you said P was the polarization density?
I believe it's, yeah.
Polarization density. Can you give us any sort of like physical intuition about what that means to a material?
So when you have an electric field in the media, it will create a dipole moment. And it's kind of the strength or the density of these dipole moments that are there. It's perhaps when you complete the wave equation with this term in it, you get a wave equation that maybe this is a familiar term in mathematics, but this would be a driven equation in that these nonlinear terms act as a source. And without these, you have zero on this side here. And that would be, I don't know what the mathematical name would be, but it's not a driven source. right? So you can see the physical interpretation of these is that these nonlinear effects are then kind of viewed as sources that help drive the electric field. So these type of questions are really good, and these are the questions that really the mathematicians need to blaze forward and really provide deep insights and being able to solve these type of equations. And so you'll notice here this is one-dimensional. If I would have used the del operator, we could have made this three-dimensional. You'll notice that there's no loss inherently in here. If there's loss, then these terms here, these chi terms, become complex variables. And if you're dealing with materials that are anisotropic, so they're not the same in all the different directions, then these become tensors. And so this is the type of mathematics that goes beyond my experience and would really involve likely computational packages and things that, and approaches that you here are probably very well aware of. So a lot of laser material processing comes down to using Maxwell's equations, the wave equations, to propagate in media, to explain how EM waves propagate in media. So a femtosecond, unless you dealt with it or thought about it a little bit, it seems 10 to the minus 15. Well, what does that really mean? It's hard for people to have a sense for that sometimes. So it's 1 million times smaller than a nanosecond. So a nanosecond is, on a somewhat older computer, the time it takes to execute one instruction. So it's like your CPU is like a gigahertz, let's say. Imagine something that could do something 1 million times faster than that, right? So maybe that makes some sense if you've thought about computers and things. Or perhaps if you consider this, light travels in 1 second around 8 times around the Earth. But in 1 femtosecond, it would move 300 nanometers, which is quite a bit smaller than one of your hairs, in fact, order of magnitude. So what we do with short pulse lasers, so another way to imagine it, if you have a pulse, this would, let's say, for example, be a nanosecond pulse, and you have a certain amount of energy, which would be, if this was time and this was power, then the integral of that would be energy, the area under the curve. And let's say you want to take that pulse and compress it, and you want it to keep the same amount of energy. Well, what would happen would be exactly this. You would get a shorter pulse with a much higher peak power. That peak power, when you focus with the laser, you get a peak intensity, and those intensities can be really high. And that's what allows you to turn on these nonlinear physics terms. Okay? So, nonlinear absorption with ultrafast lasers. So, if you look at this picture here, you'll see there's a laser coming in from the right, and it's showing you here linear absorption. You can see the laser light focus. It's being absorbed by the material, and there's kind of a fluorescence or a change in color here, and you see the shape of the beam being focused and then defocused after the focal point. On the left, coming in here, there's a very small spot here, and that is the spot where the nonlinear action is taking place. So you have absorption only in the small focus point of the lens, where the lens is focusing, and that's the only spot where you have sufficient intensities to create this absorption. And basically, here what to note is that they're using a wavelength here that is transparent, that would normally pass completely through. Like this red laser pointer here would pass through the window panes at the back uninterrupted. But if we focus it and make it an ultrafast laser pulse with red, you can actually make that glass absorb the red light. And there's some really cool things that you can do with that. One of them is you can start doing like kind of hole drilling or ablation of materials. And with nanosecond lasers, the physics of shock waves and heating and melting and ejecting material creates these much larger craters. And so it's very preferential if you go to ultrafast lasers, femtosecond lasers, you can see there's not much or any of a heat-affected zone, and you don't see a lot of cratering or material that's being deposited on top. So this is one of the examples here. There's a lot of modeling opportunities. There's also a body of work already there, but there's really, I think, work that still needs to be done in modeling these ultrafast lasers, and specifically when you start invoking bursts. So there's a concept of taking one pulse and making it into a bunch of smaller pulses that's somehow very favorable when you're processing glass, for example, to hit it with a bunch of smaller pulses rather than one larger one. And so how do you model these bursts effects? on these processes. So there's, I think, some opportunities for some mathematics and models to come in here. Here's a real example from my PhD group where they use such technology of ultrafast lasers, make it into a burst of pulses, and that allows you to really drill down into glass. And so this is, I think, about 800 or so micron, almost millimeter holes in glass with very narrow widths. And so there's a lot of very industrially relevant problems where they're trying to drill holes through glass and other dielectric materials. So this is very difficult to do with any mechanical technology. You're not going to reach these small feature sizes. And so there's really something preferential about the laser and laser technology to be able to do this. All right. So here's an example of ablation. This is of a metal. And you can see here the concept with nanoseconds. You can see here there's a lot of melted or ejected material that's coating on the surface. The feature size that you can get is not quite as small or as clean as when you do ultrafast lasers. And so this is with metal, but with ultrafast lasers, you can also do this in glass. So you can do ablation in glass. And so there's a lot of really good opportunities for industrially relevant needs for such processes. Here's another example, ultrafast laser ablation of an optical fiber. So they've taken an optical fiber and they've ablated all these square or rectangular holes all the way down to the core where the light is being guided and propagated. And this is a device that is used to insert into the human body for photodynamic therapy. So for example, if they have a cancerous tumor and they want to expose it to light because maybe they put some molecules or something that will attack only when they're illuminated, this allows the light, this structure here allows the light to scatter out around here, so they would insert this through some means, a catheter of sorts, into the human body and deliver the light to that specific area. So the novelty here is using ultrafast lasers to be able to drill or ablate glass in a precise way that maintains still the integrity of the fiber. So one of the really hot topics in laser material processing, if one looks at the literature, is spatial and temporal shaping of the beam. I'm only going to talk about spatial shaping here. So typically, a lot of beams that come out of lasers are Gaussian beams, and we continue just to focus them and they maintain as Gaussian beams. But there's a large thrust that have different types of beams. So this is a top hat beam where you make your energy profile look like a top hat, so it's uniform. It doesn't fall off as a Gaussian, it falls off as a top hat or a square. And that allows you to expose samples with a constant intensity throughout the entire sample, and there's some advantages of that. These are Bessel beams, so this might be of interest. You perhaps in your mathematics encountered Bessel functions. They're quite common in many different applications, especially in engineering. But you see these equations. Here's one where we're actually using Bessel beams to do things with laser processing. So I would say one who understands or has the capacity to understand these Bessel beams, and I'll show in the next slide, even higher ordered Bessel beams are gaining some attention as well for material processing. How do you get a Bessel beam in optics? Well, there's a special lens called an axicon lens, and it's a lens with this shape. It doesn't have this concave convex. It's got a plane, and then it's kind of like a pyramid. And then one generates a Bessel beam with such an optic. And then there's annular rings, circular rings as well. So this is an opportunity where I think models can be developed to say, well, hey, what is the beam shape that we really need to do what we'd like to do? And so I think Maxwell's equations would be involved in that, but Maxwell's equations with solutions with other functions that are not Gaussian, for example, some of these. So as I mentioned, higher ordered Bessel beams for laser material processing are gaining a lot of attention. And so how can one generate such beams? Well, there's an optical component called a spatial light modulator. It's basically an array of pixels, and your beam is incident on that device, and each one of those pixels can ideally manipulate the phase and amplitude of the portion of the wave that's incident on it. And you can do that in a preferential way to create beams of arbitrary spatial shape and spatial intensity. And so this is just a setup showing there's a Gaussian beam that hits the SLM, and then if they apply the correct phase and amplitude structures onto the SLM, they can modulate the beam to get higher ordered decibels to do that. So this is really, if you look at what they're doing, these beam shapes and what they can impart on materials, you can actually start processing with multiple spots. Maybe you could increase your throughput or make special shapes or drill a number of holes at the same time. And so here I think there's really a lot of room for modeling and mathematics to come in, understand what can be done with the technology, but how to apply, what shape should we use? I don't like going into the lab and doing this trial and error, these black box approaches, turn it on and see what happens. Much more powerful if one can model and anticipate and design and go into the lab and say, this is the type of beam we need, how do we make it? And here's why it's very preferential. So that's work that's done on the front end by folks like you guys potentially who understand math and can make these type of models. So I wanted to show one video here. Maybe I'll play it a few times. What you're seeing here is ultrafast laser pulses being incident on this same spot, and it's telling you every time there's a pulse that comes, you kind of see this other, these are shock waves. So there's an absorption. So this is probably, I'd have to look at the paper again, but the wavelength is transparent to this glass. It's being focused in. There's a damage that's being imparted, and then there's a crack that is developing. And this crack is very important. It's used, you can drill holes in this manner. You can line these up and cut glass with this. And this is an a common experiment in physics that's called the pump probe experiment. So they would put their laser pulse that's meant to do the process, and they follow up very shortly after with another pulse that illuminates, and it's kind of like your flash for your camera, and illuminates the process. And so I'm showing you the results of this, and you can see the thermal shock waves that we're propagating. There's an opportunity for, and I'm sure the field is already looking at this, and there's probably a body of literature, but there's really some opportunities in doing modeling of the dynamics that happen when you focus light here. You saw that there's some really interesting physics that are happening. There's these shock waves. Not shown here, there's actually a plasma that develops when you start this process as well. And so there's other techniques.
Are the problems more in the models or in the actual computations that you do to compute solutions to the models?
So the question is, where should, I think, maybe the effort or thrust of the effort be right now? Is it in building the models, or is it in the mathematical techniques that are used to solve those models? And I must be honest, I don't know that body of literature enough. But what I can say is, in my experience, I don't have something that I can go to and say, this is how I should apply the beam, and this is the number of pulses I should use, this is how far they should be spaced. We're starting to understand that, okay, certain physics will happen on picosecond time scale. Some of these shock waves and things will happen on maybe nano to microsecond time scale. But I'm not aware of models that are really truly representative of what needs to be done to create an industrially robust process. And I'd like to see some of that. So I don't have a full answer to your question, but it could be either or both. I'm not aware. So here's another really interesting thing that you can do. It's called two-photon polymerization. So if some are familiar with the semiconductor industry and the concept of lithography, so you'll have a material, and then you'll deposit a layer called a photoresist, and then you'll expose that photoresist to light in certain areas and not in others. And the areas that get exposed to light, there's a chemical reaction that takes place, and it hardens, and then there's a development stage, and you can remove that, and you make these different patterns. This is how they build integrated circuits. And so you can do this using multi-photon absorption, or in this case, two-photon polymerization. And so that allows you to only trigger this light absorption where you put your focus. So you can do this in 3-dimensional. So this is like 3-dimensional lithography, truly 3-dimensional. The semiconductor industry likes to do planar and then stack a bunch of planar and build that up. And they call it 3D at the end. Okay, fine. Here's a 1-step 3D lithography process. I'm showing some kind of really interesting examples that, for me, this is an optical fiber. It happens to have 4 cores, so there's 4 locations where light will guide through this fiber. And they want to connect that to another chip, another optical circuit. And so here, they would have put this polymer overlaid over top and come in with the laser, and the laser would have traced the area from here to here. And that area, and only that area where the laser beam was focused and traversed through, would have gone through that chemical reaction that hardens the material, and then they could develop it and wash it away. And so here, this is kind of photonic wire bonding. So we're trying to move away from electrical wire bonding and electrical circuits that, while are very good at switching things, have trouble with interconnects and heat dissipation and the rate at which they can you can modulate these signals. So optical interconnects are an area of active research, a hot area. So this is one way of doing them. This here is a much more complicated structure. It's actually a photonic crystal. It's, if you're familiar with that, if you're familiar with semiconductors, this is kind of like the optical equivalent, where such a structure here will have an optical band gap or a photonic band gap, a region where certain wavelengths cannot propagate. And so there's a lot of modeling that is done here to explain electromagnetic wave propagation through a periodic, 3-dimensional periodic medium. And some of the techniques that I'm familiar with are either plane wave expansion technique or finite element methods or FTET techniques as well. These are probably, I expect, common tools that you guys probably are aware of. Some of you probably use it very routinely to solve equations. And so designing what shape this should have in order to get a band gap at a certain desired wavelength or a desired width is also a very powerful tool. And so what I'm showing here, there's a laser way of actually making these, and it's so flexible that even if your models would predict really, really kind of crazy or crazy in the fact that very difficult structures to make, I think this technology is poised to do that. And don't forget, with these nonlinear interactions, you can get feature sizes that are smaller than the diffraction limit of light, so potentially smaller than the wavelength of the light that you're using. Here's one more example of this 2-photon polymerization. This is a needle, a fiber optic, an optical fiber that's been put through the syringe part of the needle. And what they've done here is they've built a lens on the tip of this fiber. So they want to insert this into the human body and do imaging, but they want to have a lens here. And this lens here is actually a triplet lens, which means there's 3 lenses that have been stacked together. And they do that to correct for these higher order aberrations that one encounters when you try and see through different media. And so using this 2-photon absorption mechanism, they were able to put a droplet of polymer and then laser scan and harden this material, develop it, and have this triplet lens design on micro scale. So you can see the 100 micron scale bar here, building micro optical elements this way, and building it on the tip of an optical fiber that will then be inserted inside the human body for imaging. And also Friday afternoon experiments. I guess graduate students like to have fun, especially on Friday afternoons. When you discover these new technologies, you have to do something cool. So this is at the time of publication, is what the world's smallest bull. And so if you Google this, you'll find spiders, the Eiffel Tower, Leaning Tower of Pisa, all kinds of crazy shapes. So it's kind of like 3D printing, right? But with laser technology. You can do this really, really small. And this is in polymers. All right, so we go now into the area of expertise from my doctorate, and that's refractive index change. So if you recall back to the nonlinear equations, there's a term called chi3, which is responsible for giving you a intensity-dependent refractive index change. So you can change the refractive index of a transparent material by focusing really intense light into it. And so showing here, this was a block of glass, in this case fused silica, and when you have these femtosecond laser pulses and you focus them very tightly, you can actually change the refractive index of the glass locally only in that focal point where you've tightly focused the laser. And so if one moves the beam and the glass block in relative motion, you can then trace out different patterns. And as shown here from a top view looking into the glass, this bright white zone here is an increase in the refractive index of glass. And so this is actually an optical waveguide. So a waveguide is kind of like your optical fiber. Optical fibers are really great for bringing encoded light signals from here to San Francisco, for example. But to bring an encoded light signal on an optical chip from one spot to a few hundred microns away, and by the way, it's got to bend and go out of plane to get there, this is a 3D writing technology that allows you to make optical circuits. This first demonstration was in 1996, and since that time, they've done many more complicated optical circuits and systems in a wide variety of dielectric materials at many different wavelengths. And so my PhD project was the following. I said, well, people are doing this refractive index change stuff, and they're always using these like bulk glass plates. And I thought, okay, well, then I also was familiar with optical fiber, and I thought, well, the optical fiber is kind of not that smart a device. It's a passive device. It brings light from point A to point B. It's totally revolutionized modern communications. But in fact, it's just carrying light from A to B. And I thought, well, the active part, the only part that carries light is in this core here, and that's about 1% of the entire area. And I asked myself, well, could I build optical circuits inside fibers? Could I use this technology to do that? And the answer was yes. And I'll show you a few things that I've done. This is the change in refractive index of blow up of here. This is a waveguide that is written along the fiber beside the core inside the cladding here. So kind of, we call this cladding photonics, or making really smart devices in our optical fibers. And so one of the questions I had to answer is, well, as light is coupled into and propagates along this core, how do I get light out of that and bring it into the cladding? And then what kind of interesting things can I build in the cladding? And so I developed a variety of ways. I was successful in bringing light out of the cladding and putting it back in the cladding. And so in this part here, we get into less of the fundamental physics modeling, but there's opportunities here to model more passive or even active optical devices. So for example, like directional couplers. I heard someone here, or there's a course, or someone's doing research on coupled oscillators or something like that. So the coupling between optical waveguides, I think, would have some analogous equations and things. So there's opportunities in developing models and predicting behavior of what this should be. One thing that I really like is a model that could predict or explain what the shape and the magnitude of the refractive index change that's imparted with a certain set of laser parameters. So this is a very industrially relevant, like build one, but how do you build 1,000, or how do you build this in a reproducible way? We really need to build and walk towards models that can predict and explain what's going on, which would allow us, oh, well, I wrote something, I expected this loss, it's not that loss, okay, well, what do I do? What went wrong? If we can start getting some models to that end, and that's, I haven't thought about how to do that, and it's probably not my core skill set to do that. I wanted to show you one example of a device that my colleague, Luis Fernandez, and myself built using this. We built a waveguide inside the cladding, and we built a helical waveguide inside here. So we built an optical tap. It pulls a little bit of the light out of the fiber core. It propagates it along a waveguide that does a helical shape, and then it connects it back into the fiber. And so there is an optical path length difference between light that's in the core and light that's in this waveguide that we wrote. If you recombine two light waves that are not in phase anymore, you'll get an interference pattern. And we're showing that here with broadband light. You can see that there's this interference pattern, you have a series of highs and lows, so constructive and destructive interference. And it turns out that if you apply a torsion force in one direction, you will wind up that spiral. And if you reverse the direction of that, you'll stretch that one. And so the optical path length difference between these two devices changes. And so we decided to make an experiment with that. So we have a piece of fiber that's held here, kind of like a pendulum, and we spun this. And you can see when it spins, if we look at one wavelength, we see the intensity change. So from this plot, you can tell exactly how much force, torsion force there is. And you can also tell which direction it's been applied, because it's either stretching or compressing. And so this was a way now where we're starting to make fibers be able to do a lot more than just carry light from point A to point B. So this would be like a fiber sensor of sorts.
How much are you changing the path length of the light when you are producing it?
Yeah, so how much are we changing the path length? It has to be enough to get a 2 pi phase difference, but it's probably many multiples of 2 pi phase difference. I don't have the exact numbers. In my thesis, or in this paper actually, we would have that. But that raises one important question, would be maybe what's the percentage refractive index increase that you gain with this technology? And typically about 1% increase in the refractive index is what's routinely achievable, let's say. To give you an idea, the refractive index between the core of a waveguide and its cladding is 0.03%, so it's quite a bit less.
And sorry, just
Yeah.
from a material standpoint, what's the actual phenomenon that is changing that refractive index? Is it just the heating of the material via the laser that kind of...
So yeah, very good. These are the exact questions I'm happy to hear applied mathematicians asking, because these can lead to really good models. And maybe these already exist, I'm not sure, but this is really good questions. The question is, what's really physically happening in the glass to create this refractive index change? Complicated question, there's many theories, but I'll give you the Cliff Notes version of this. Ultrafast lasers are focused into the glass. There's this nonlinear, or third order nonlinearity, optical Kerr effect, if some are familiar with the physics. There's an intensity dependent refractive index change. So there's an absorption of multiple photons simultaneously. You get a free electron. That free electron will continue to gain energy in the incoming laser beam that will oscillate. It'll hit other electrons, and through collisional ionization, you'll get many, many electrons to create this superheated plasma. And this plasma transfers energy to the lattice, to the material. And there's different theories as to what happens. One is that there's color centers or defects that are imparted in the material, and that can change the refractive index of the glass, much like inserting a dopant or something into a material will change the refractive index. There's some evidence against that, in that if you bring the glass to annealing temperatures, those defects would wash out or anneal out, and yet the refractive index change still maintains there. So it's not completely that. The other theory says, well, you're rapidly heating up this material and then cooling it again. So there's kind of this thermal redistribution effect that happens, and that can somehow change the refractive index. There's some evidence to support that, and there's other evidence that it doesn't work like that all the time. I think the literature suggests the most prevalent is that there's this explosion or this shock wave that happens, and there's a recompaction of the material, redensification of the material, if you will. And that is one of them. It's material dependent, and it could be some contribution of each of these three things that I mentioned working in tandem. But I see somewhat in the literature that this compaction or redensification of the material has been quite well used to explain what we're seeing. Yeah. So there's a lot of really interesting physics that models that goes a little bit beyond my previous experience. And so, and lastly, the concluding remarks that I have for this talk would be that black box approaches, walking into the lab and turning knobs, will gain 10% improvements. But if you really fundamentally understand something, you'll get 10x improvements. And that's where we want to operate, right? As graduate students, as industry folks. Generally, we want to make revolutionary changes, not evolution. We want revolutionary changes, And that comes from fundamental understanding. And it's been my personal experience and observation that I think the funnest and perhaps most remarkable breakthroughs occur at the boundaries or the frontiers of different areas of research and where they intersect. And that involves collaboration. And I see a lot from my outsider perspective on this faculty of applied mathematics, or even conceptually applied mathematics, have an important role to play in both of these. Building fundamental understanding and working with others to really solve fun and remarkable problems. And so a little bit of encouragement, I would really motivate you guys to think about not only my talk, but as you go on and study mathematics, how do you apply this and what kind of things that you can solve, who to collaborate with. I think there's really a lot of exciting opportunities, and I'm just happy to share my little bit today on laser material processing, specifically ultrafast lasers. And I would thank you very much for your attention, and also to Alex Townsend, who invited me here and suggested this talk, and Eric has provided a lot of support to make this happen. So thank you very much, and to all of you. Really appreciate it.
Thank you for a wonderful talk. Do we have any questions for Jason now?
In one of the images you showed, the pulsing laser was developing a crack into the material. How has that, I mean, that crack is probably pretty important. How has that been leveraged, I guess, or dealt with in terms of not messing with your whatever application you're trying to use it for?
Right, so that crack has typically been advantageously employed to, if you scan that all together, you can link up the cracks, and that allows you to cut and separate glass. So there's a lot of papers in literature that show this, in fact, method of glass cutting. So, yeah.
If you're doing more sensitive, per se, like kind of printing or etching on the glass, does that crack get in the way of what?
So if you wanted to mark, so you saw in the video, so the question is, does that crack always have to be there, and does it interfere with some of the applications? If you recall the video, that crack only developed after a certain number of pulses were coming in. So there are regimes where you can work where you can get a defect, but not necessarily a long crack there. So yes, that can be tuned. And there's applications for perhaps hole drilling where you would not want this huge crack. You want just a hole, a crater that goes through. So the answer is yes. And there's ways of doing that, reducing power, or just in some way where, in the example video we saw that crack developed after a certain number of pulses in a burst were applied, but not initially.
So back in the start, you were kind of describing how you could try to do these kind of very exotic but beam profiles.
Yes.
Where you take the Gaussian beam and then you bounce it off of some sort of pixelated comparison. So in the slide you showed some very specific patterns which seem to have some kind of geometric connection, where you have like some peaks, and then you have like 4 peaks and then 5 peaks. Yeah, right there. Is the method general in the sense that if I were just to take some arbitrarily designed SLM or some specifically designed SLM, I could recreate some of those shapes of interest, like the top hat profile, or and then presumably this is all.
Yeah.
This is all exists. Yeah.
Yeah. So these are higher order pixel beams. That's just one example. So the question is kind of what can you really do with the SLM? And can one walk in there and make, for example, a top hat beam or something? And so what you're limited is the number of pixels that you have will dictate the kind of resolution that you can modulate your incoming laser beam. Another technology to do kind of the same thing is a deformable mirror, where you have a mirror surface that's like a micro electrical mechanical system, and there's little push-pull pin actuators underneath, and then you can shape this mirror. And it's very commonly employed for aberration correction. The mathematics behind there, if anyone's encountered Zernike coefficients or Zernike polynomials, these type of polynomials exactly describe the types of aberrations one encounters in optics. There's first order, second order, third order, spherical aberration, trefoil, all these kind of things are really nicely modeled by Zernike coefficients. And so by understanding what Zernike coefficients you need to do, you can then start designing what this phase pattern needs to look like, and you impart that phase pattern on the SLM. And so I think an active area, and one that really I think requires mathematical expertise, is how to get these shapes, and then what phase to put on there, and what shapes will interact with the material in the way that you do what you want to do in the most efficient and preferential way. So SLMs can routinely do top hat profiles, higher order beams, best beams that we're seeing, all kinds of things, arbitrary shapes. So there are limits in terms of the number of actuators or pixels that you have, and the wavelengths of operation, and some other things. But it's generally a very flexible and powerful tool. In my prediction, we see a lot of this in academic papers. I haven't seen a lot I've seen some in the patent literature. I expect that spatial and temporal shaping of pulses is a really powerful knob to start building fundamental understanding for laser processing. Yes. Yeah.
I have a question that I'm not sure how well formulated it is about the corporate culture.
Sure.
And follow up on the earlier question that I asked. Suppose someone is trying to solve a problem, do a computation, and it's not working. Then there are several different approaches that you can take in order to try to overcome that. You can say, well, the model's too complicated. Let me see if I can make simplifications that don't really do violence to the physics that I'm trying to deal with, and see if I can solve a simpler problem that will be adequate for what I want to do. It's also possible that you look at it and you say, well, the algorithms that we have just aren't good enough to solve this kind of problem. And I really have to go back to the drawing board and do some more mathematics in order to develop better methods. That tends to be a slow process. And whether in an industrial environment you have the patience and the resources in order to support someone to do that, and whether you can identify the crux of the difficulty so that when they're trying to approach things from a mathematical perspective, that they're really getting at the crux of what the issue is something that requires a lot of communication in order to make work. And I was wondering if you can comment on what happens within Corning when you're faced with that type of situation.
Okay. So I've been with Corning for about 1.5 years, so that limits a little bit of my scope, but here's kind of my sense. Let's say, I'll give you one example, I'll come back and explain a little bit more. Gorilla Glass, this process of ion exchanging or chemically strengthening glass was developed some 40 years ago. And it was shelved because it's different from what you're asking, because I don't think it was shelved for a technical reason. It was shelved because we don't know what to do with it. Well, it turns out, I think mostly the cell phone market said, hey, we need strengthened glass. And Corning had something on their shelf for 40 years ago that commercialized, that's Gorilla Glass. What do we do when you encounter a barrier and things potentially are shelved because of a technical barrier where there's no customer pull or resources to continue that? I'm an academic, you saw my CV, I think that's a pity if that happens. What I can say is that I know Corning spends a lot of money on R&D, And they've been around for over 165 years and have done some really revolutionary type things, the optical fiber, the Edison light bulb, a lot of things. And I think you have to be willing to take those risks and say, it's not there yet, we have to keep investing in this to make it happen. So that's what I hope would happen. I guess I need to be at Corning more to see if that happens. But being practical, is there,
I mean,
are there projects that get stopped? Most definitely.
It seems like, I mean, if you, in the history of industry in this country, there are places like Bell Labs being probably the most notable example, that for many decades were places that were renowned for devoting resources to doing these kinds of things. A very vibrant interaction between the technologies that were being developed in those environments and the applied math community. Many of those places are pale shadows of what they were 30 or 40 years ago. And you're giving the impression that that's not the case at Corning. That Corning is still willing to make the investments that are required for long-term breakthroughs in these sorts of things. And
That's generally my impression. I'm not saying that everything that starts never gets canceled. I think there's business decisions, but my sense is that Corning really values R&D.
Yeah.
And that's been my personal experience there.
And if someone approaches you, if one of the students approach you when they're finishing their degree and say, hey, I've developed this expertise in numerical analysis. I don't know beans about lasers yet. I can learn. But I'm interested and I think my skills might be useful. Is there a process for talking in depth with individuals like that to see whether it is a good match?
Yeah, I'll answer your question in two ways. I will say that my team, my laser processing and engineering team, has two recent hires, both young ladies from chemistry at Cornell, and they did a little bit of laser spectroscopy. And they have used an ultrafast laser. I would not consider them out of school laser processing engineers. Our team, I think, really values this diversity of different backgrounds. And we have, one of my colleagues also is quite strong in kind of more modeling. And the number of software packages that he knows how to use very proficiently is quite high. And some people have a lot more experience in one area or not. The point is, my team seems to be very diverse in the background, and what the message that I see is that you don't have to be a femtosecond laser expert to be employed in even our direct group. There are certain things that can be learned, but we want to see core expertise in some area. And I know Corning does have people that does optical modeling. And so where to start that conversation? I haven't been there long enough to see the inroads there. There's definitely job postings, but I'd be happy to talk with folks that are graduating about if they have an opportunity or they want to see something or talk about what potential opportunities are there. I could find out internally what process. I know we do hire interns, PhD and master level students during the summer, so there's a program. I don't know I helped co-supervise a student last summer. I wasn't involved in the process of hiring and getting the students, so I don't know how it all works, but there are programs like that.
Thank you.
Okay, one last.
I have a question about research and industry too. So, it's Corning's interest if a breakthrough is made that they be able to profit from the breakthrough, so they try to hang on to that. Academics tend to like to see their breakthroughs widely disseminated, and there's some tension there. So could you address that? How you have experience working with people in academia and having
so this is something that I struggled with because I came from academia, and I just loved going on the conference circuit and presenting very proudly the great work that I had done. And when I joined Corning, I realized that, you know, in a company setting, and actually I saw this near the end of my PhD as well, because I did file a patent application on some latter part of my doctoral work. And so I started to get a sense of that there, but really I was it wasn't in my nature to hold back when I started working at Corning, and I'm slowly learning that one does need to, according to the company's policies, we don't divulge everything. There's an order in which, and a way in which things do get disseminated, and first and foremost, it would be to file any patent-related aspects of that work, and then that eventually would become public in some form, and then perhaps there would be an opportunity for conferences or information. A lot of my colleagues routinely go, there's Photonics West that's happening, it's either wrapping up or just starting, and I know personally a few colleagues that are making presentations there, so Corning does make presentations at conferences. Like I mentioned at the beginning, there is a process that would go through for what would be disseminated. Yeah, so I guess in the end, for me, it was a big change. I understand the need on both ends. I really want to see information get out there, but the company also needs to somehow make its living on and fund new initiatives. So it's a tough one. It's a tough one. Yeah.
Yeah, I've done some consulting for Corning, and I have a little section on my CV that says reports 1 through 6.
Yeah, restricted
That's-
reports.
That's
Yes.
about where it stands.
Yes.
Corning one.
Yeah. So Corning has an internal reporting system where you can, almost like academic papers. And so when your professor or colleague here is mentioning that in his collaborations, he's author or co-author on some of these reports.
Okay, I think we should continue the discussion in the other room. We have some refreshments there. And I would particularly like to encourage the undergrads or graduate students in the room to talk to Jason.
Please, I'm here for as long as you guys are. Well, maybe not as you guys. Interesting. It is Friday. I'm here for a while.